In this video, we will look at the use of carbon 13 NMR and how it can be used to identify an unknown compound. Carbon 13 nuclear magnetic resonance, or NMR, is a type of spectroscopy used to identify the number of carbon environments present in a compound and the types of bonds present. This type of spectroscopy is concerned with the magnetic properties of carbon 13 nuclei. About 1% of all carbon atoms exist as carbon 13, whilst the rest are mainly carbon 12. Unlike carbon 12, carbon 13 nuclei behave like little magnets, which can either align with an external magnetic field or against an external magnetic field. It is possible to flip the nuclei to align with the magnetic field if sufficient amount of energy is applied. The energy needed to make the nuclei flip depends on the strength of the external magnetic field used, but it is usually in the range of energies found in radio waves, so about 25 to 100 megahertz. It is possible to detect this interaction between the radio waves and the nuclei as a peak on the graph. The x-axis of this graph or spectrum is called the chemical shift, and it's measured in ppm, which is parts per million. The peaks represent the number of carbon environments in the molecule. So as you can see in this molecule, there are 3 carbon environments. It's 1, 2, 3. Where the peaks for the carbon environments appear along the x-axis depends on the types of bonds present, which we'll look at a little bit later on. For now, if we have a look at the carbon environments, you can see that this molecule, which is methanol, only has 1 carbon atom. This carbon atom here is bonded to 3 hydrogen and an OH group. Therefore, it's only got 1 carbon environment. 1 carbon environment means on the spectrum it's going to have just 1 peak. Here is ethanol. You can see that this carbon atom is bonded to 3 hydrogen atoms, a CH2 and an OH, whereas this carbon atom is bonded to 2 hydrogen, OH and a CH3. Therefore, there are 2 carbon environments, so on the spectrum you'd expect to see 2 peaks representing this. Here we have propanone, a ketone. You can see that these 2 carbon atoms on either side are in the same environment, whilst the carbon atom in the middle here is in a different environment to the other 2. This means that even though that there's 3 carbon atoms in the molecule, there are only 2 carbon environments. They're the 2 that's the same. This is the one that's different. On the spectrum, this would represent 2 peaks. Note that the peak that represents the carbon atom that is bonded to the oxygen is further upfield than the other. This is due to the electronegativity of the oxygen atom, which we'll look at in more detail a little bit later on. Here we have propan-1-ol. You can see that none of the carbon atoms here are in the same environment. This carbon atom is bonded to 2 hydrogen, OH, then CH2CH3. This carbon here is bonded to 2 hydrogen, CH2OH and CH3. This carbon here is bonded to 3 hydrogen, CH2, CH2OH. So they're 3 different environments. On the spectrum, therefore, you would expect to see 3 peaks, each representing the different environments. Again, note that the peak for the carbon-oxygen is upfield to the other peaks. Lastly, we have propan-2-ol. Here you can see that the two carbons at either end of the molecule, these two here, are in the same environment, whilst the middle carbon here is in a different environment. These two are the same, the green one's different. This translates to two peaks on the graph. Let's look at pentane. You will notice that pentane is a symmetrical molecule, so therefore has three carbon environments. A structural isomer of pentane is 2-methylbutane. Remember that structural isomers are molecules that have the same molecular formula but a different arrangement. Due to the arrangement of the carbon atoms in 2-methylbutane, you have two carbons that are in the same environment, which will be this one and this one, whilst the others will be in different environments. Therefore, you will have a total of 4 carbon environments. Looking at the isomers of propanol, we can apply the same approach. Here we have propan-1-ol, which has 3 carbon environments, whilst the symmetry of propan-2-ol results in 2 carbon environments. As mentioned at the start, carbon nuclear magnetic resonance can not only indicate the number of carbon environments present, but also the type of environment. Here is a list of the type of environments and the chemical shift. You can see that the carbon-carbon single bond has a chemical shift of around about 0 to 50 parts per million, whilst the carbon-oxygen double bond has a chemical shift of about 150 to 200 parts per million. Why is this? Well, the effect of the magnetic field can be influenced by the number of electrons surrounding the nuclei and the types of bonds involved. To start with, let's look at bonding electrons. Bonding electrons surrounding a nucleus results in the nucleus not feeling the full effect of the magnetic field. So in order to flip the nucleus, you would need to increase the strength of the magnetic field to compensate for the electron shielding. So if you have a carbon atom which is bonded to an element which is more electronegative, for instance oxygen, then the electrons would be drawn towards the oxygen atom. This is called electron withdrawing, resulting in the carbon having less electron shielding. This means that the carbon nucleus would feel the full effect of the magnetic field, so the nucleus would be easily flipped. So if you have a carbon atom which is bonded to an element which is more electronegative, for instance oxygen, then the electrons would be drawn towards the oxygen atom. This is called electron withdrawing, resulting in the carbon atom having less electron shielding. This means that the carbon nucleus would feel the full effect of the magnetic field, so the nucleus would be easily flipped. Let's have a look at this as an example. You can see on this spectrum of these two compounds. The oxygen is more electronegative, so it draws electrons away from the carbon atom. This results in the carbon nucleus having less shielding. This means that it will experience more of the magnetic field and it has a greater chemical shift, so it appears more to the left on the spectrum. Just like infrared spectroscopy, you'll get a data table in the internal to use. Along the bottom, you can see the parts per million value. Note the chemical shift here below 20 parts per million relates to the CH3 environment in the compound. From 20 to 50 parts per million, you're looking at the presence of a halogen. Around 180 to 220 indicates the carbon-oxygen double bond environment found in things like aldehydes and ketones. Here is a spectrum for the ester ethyl-phthanoate. In the internal, you would be expected to note that there are 4 carbon environments. You will notice a peak just below 80 parts per million with the label CDCl3, which is just here. This is used as a reference peak, so you can ignore this peak. You would be expected to note that peaks 1 and 4 are 20 and below, as they represent the CH3 environments on either end of the molecule. So this is the CH3 for peak 1 and the CH3 here for peak 4. Next would be the C3 environment, again further upfield due to a reduced amount of shielding created by the neighbouring oxygen attracting the electrons within that carbon-oxygen bond. So here's your 3rd carbon with the carbon-oxygen bond, which represents this C3 peak. The C2 environment is at 170 parts per million. This is due to the neighbouring oxygen atoms attracting or withdrawing the electrons in the bond, resulting in a greater chemical shift for that C2. So what would you need to write for the internal? If we refer to our previous spectrum of the ester, you would say, in the C NMR spectrum provided, there are 4 peaks, so therefore the compound has 4 different carbon environments. The peaks at C1 and C4 are around about 20 parts per million and below, as they represent the CH3 environments at either end of the molecule. The C1 is higher than the C4, as it is closer to the carbon-oxygen environment. This results in the nucleus not being as shielded as the C4 environment. The C3 environment, again, this can be found further upfield at around 60 parts per million due to the reduced amount of shielding created by the neighbouring oxygen atom withdrawing the electrons within that carbon-oxygen bond. The C2 environment is at 170 parts per million. The neighbouring oxygen atoms are withdrawing the electrons in the bond, resulting in a greater chemical shift for the C2 carbon environment. Remember, just like infrared spectroscopy, you are expected to note at least 3 points about this spectrum, and in some cases, it may be the absence of peaks that you are noting.